Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. In this episode, we're joined by Nina Miolane, researcher and lecturer at Stanford University. Nina and I recently spoke about her work in the field of geometric statistics and machine learning. Specifically, we discussed the application of Riemannian geometry, which is the study of curved surfaces, TWiML. Riemannian geometry can be helpful in building machine learning models in a number of situations, including in computational anatomy and medicine, where it helps Nina create models of organs like the brain and heart. In our discussion, we review the differences between Riemannian and Euclidean geometry in theory and practice, and discuss several examples from Nina's research, which is a Python package that simplifies computations and statistics on manifolds with geometric structures. Before we dive into the conversation, I'd like to send a huge thanks to our friends at IBM for their sponsorship of this episode. Interested in exploring code patterns, leveraging multiple technologies, including ML and AI? Then check out IBM Developer. With more than 100 open source programs, a library of knowledge resources, developer advocates ready to help, and a global community of developers, what in the world will you create? Dive in at ibm.biz/MLAI podcast, and be sure to let them know that TWiML sent you. And now, on to the show. All right, everyone, I am on the line with Nina Miolane. Nina is a researcher and lecturer in machine learning for computational anatomy at Stanford University. Nina, welcome to This Week in Machine Learning and AI.
Hello. Hello, Sam. Thanks for calling me today. And hello, everyone.
Absolutely. So, let's just start with a little bit of background. And in particular, you started out in theoretical physics. How did you make your way from general relativity to machine learning?
Yes, that's correct. I started with theoretical physics. I did my master in theoretical physics and mathematical physics, which I think, yes, it might be an original background for someone in machine learning these days. And so, initially I was looking at different mathematical models of reality, specifically at the infinitesimally small and the very big. So I was looking at models of particles, elementary particles, and their collisions at very high energies, and also at models of the very big, like the stars, the galaxies, space-time, and all these things. And so, yes, I had courses like general relativity, black holes. And this was very interesting because after my master, in fact, I moved to machine learning for the medical imaging field. And at that time, a lot of people asked me the question, like, what does it have to do with machine learning now? Why are you switching? What's the link? I started a PhD in machine learning, and how could I do that after a master in mathematical physics? And in fact, both fields are really related. And the main link they have is geometry. So in theoretical physics, when I was looking at space-time, in fact, I was looking at the geometry of space-time. So you might know that Einstein in the early 90s used geometry, actually a particular kind of geometry, which is called Riemannian geometry. And so Einstein used geometry to describe space-time and how the geometry of space-time was changing depending on the massive objects that are in space-time. So for example, if you go very close to a black hole, then time will slow down. And so the geometry of time near the black hole is changed. So geometry has a lot to do with with the mathematical model that you put in theoretical physics. And then between my master and my PhD, I went to computational anatomy. So medical imaging, I was looking at organ shapes. And here again, I got to do a lot of geometry and Riemannian geometry. Because in fact, the data in machine learning that I was looking at are geometrical data. So they live in a space, in a data space, that also has a particular geometry. And so I was studying the geometry of this data space just in the same way that I was studying the geometry of space-time during my master. So that's how I got from theoretical physics to machine learning for data belonging to these geometric spaces. And then after that, I kind of stayed in machine learning. So I was a software engineer for a little bit in a machine learning startup. And now I've come back to academia, and I'm now a postdoc at Stanford University, as you said it. So, and from my PhD to my work in software engineering and my postdoc, through these three stages, in these three steps, I was looking at data belonging to geometric spaces. And these data have been mostly organ shapes. So you said it, I'm in computational anatomy. So I built computational models of the human body. And so the data I have are organ shapes. During my PhD, I looked at brain shapes and how brain shapes vary when you have a disease, for example, Alzheimer's disease or other forms of dementia. When I was a software engineer, I look at heart shapes. So how the shape of your heart may vary if you have different cardiovascular diseases. And now back as a postdoc, I do two things. I look at brain shapes again, but I also look at the shapes of abstract data spaces. So that's how, I'm kind of merging all the geometric background that I have gathered to come to the field of machine learning.
Maybe we should start from the beginning and have you explain what Riemannian geometry is and how is it distinguished from the Euclidean geometry that we tend to think of?
Yes, sure. So Riemannian geometry is this theory of mathematics that allowed Einstein to describe the geometry of space-time. And actually, it's a very powerful mathematical theory, which is why I think Einstein has used it to describe this very complicated space. And it's a generalization of Euclidean geometry. Actually, Riemannian geometry is locally Euclidean. So let's take an example. If you consider the Earth as the planet, you look at the surface of the Earth locally. So for you and me in a given room, in a building, locally, the geometry is flat. It looks like we live on a flat two-dimensional plane.
Mm-hmm.
But if you look at the global geometry of the Earth's surface, it's a sphere. It's a 2D sphere. So the geometry is in fact curved. And
no
that's
way.
What... Yeah, I know, right?
I'm just trolling the flat earthers out there. Sorry.
No. But that's a simple example to explain the generalization of Euclidean geometry to Riemannian geometry. Okay. That's one example that everybody uses because it's more intuitive for everybody. But it describes very well actually what it is. So Riemannian geometry is locally Euclidean, but if you look at the global shape of your space, then it's going to be curved. And when you start to do statistics on the curved spaces, then actually everything that we know about usual statistics breaks down. So let me come back to the example of the Earth for a little bit, and then we'll go into other examples if you prefer. But for the Earth, imagine you take two cities on the surface of the Earth, and you want to do statistics on the position of these two cities. So very simple example. We have only two data points. And an example of statistics that you may want to compute is, for example, an average in position of these two cities. If you use usual statistics, so statistics in Euclidean space, you're going to compute a city that will be in between the two cities that you have on the surface of the Earth. But this city, if it's the middle of the chord joining the two cities that you have on the surface of the Earth, the average city will be inside the Earth.
Right.
It will not be on the surface of the Earth. And so you're in a situation where you want to compute an average of cities that cannot possibly be a city because it's not even on the Earth. And that's a very simple example again, but that's a very, very important example because it shows that if you do statistics for data that belongs to curved spaces, even the very definition of mean cannot apply because the very definition of mean is a linear definition. The mean is a weighted sum of the elements, so it's linear. Applying this linear definition to a nonlinear space, this completely breaks down. And that's why we got into developing this new field that we call geometric statistics. And we are asking the question, how should we generalize everything that we know about statistics to these curved spaces.
When we're thinking about geometric statistics and Riemannian geometries, are we exclusively looking at statistics as it relates to the points on these curves, as opposed to the relationships between different curves, for example?
Yeah, so when we look at geometric statistics, we mean statistics for data that belong to these curved spaces. But actually, you can look at curves on these curved spaces, and the space of curves on curved spaces is also itself a space that is non-linear. So you can look at different kind of data space, and as soon as you have something curved somewhere, it's going to propagate, and you're going to have some geometry somewhere.
Hey, I think the thought that was the origin of that question was trying to apply this to your computational anatomy types of problems. I'm imagining in those fields, yes, I'm interested in describing statistically the surface of the heart, but I'm also interested in things that are happening within the heart, and maybe there are complex surfaces that are composed of different things that are easier described with multiple curves as opposed to a single curve. So maybe you can use that as a segue to explain how this is applied in that field.
Yes, so for sure, there are two types of geometry that you can consider when you talk about these geometric objects like the surface of the heart. First of all, you can take one heart and look at its surface, and this surface of this one heart will have a particular geometry. But I'm not looking at one heart and the surface of one heart. Actually, I'm saying, in the way we model things currently, I'm saying that this heart is just a point in a very high-dimensional space, abstract space, that represents its shape. So the shape of the space I'm looking at is the shape of the data space. So actually, for example, if you go back to the example of the heart, imagine you have a heart and you want to study its shape. What we usually do is that we say, okay, the shape of this heart is actually going to be the deformation of a template heart. So we assume that there is a template shape that is, for example, the healthy heart shape. We fix that, and then we represent each patient heart by the deformation of the template shape to the patient shape. And so now each heart shape is represented by a deformation. So one data is a deformation. And so if you have different patients, each of them is represented by the deformation from the template heart to their heart. And so your data are these deformations that are points in a high-dimensional space, which is the space of deformation. So it's a bit more abstract than looking at the surface of one heart. It's actually one data is a deformation from a template to the patient space, and the space of data is the space of deformations, which is curved.
Okay. I think I'm following here. So a question that pops up for me is, I can imagine representing these, a particular heart, a particular deformation as, some set of parameters that kind of describe in the physical world, how the heart is deformed from the template. But I can also imagine something more abstract, kind of like an embedding applied to, this heart space.
Yes.
Does that concept apply here?
Yeah, that completely makes sense. So I think initially people were looking in physical models, like mechanical models, and imagining which clinical parameters may control the deformation from a template heart shape to a patient heart shape. But then there are so many parameters that you can learn, and maybe you're not going to find all of them. And then even if you find these clinical parameters that govern the transformation from a heart shape to another, then how do you translate that to the next organ shape? You will need to do that all over again to do a deformation from a healthy brain shape to another brain shape. And so in our case, we are more in the second scenario that you've described. We just look at the abstract deformation and we parameterize it just in terms of geometry. So this deformation, this point in our curved space, we represent it mathematically as a diffeomorphism. And then we look at how many parameters we need to describe this diffeomorphic transformation. So we look at that in the abstract way. And also because, I don't have a medical background, so I come from a mathematical background. So I think that's also a reason why we use our mathematical tools to describe transformation. Now, the hope is that eventually both fields will merge together. So by describing these transformations, these deformations of organ shapes, of heart shape, by mathematical or geometric parameters, maybe by doing so, we will discover new clinical parameters. And actually, we started to see a hint of that when we did a study on heart shapes. So we had many hearts. We gathered many heart shapes, a data set of many heart shapes, and we performed a principal component analysis on these heart shapes by using deformations. So we were looking at what were the main variations in terms of geometric shapes within these heart shapes. And the main variation, geometric deformation that we found was the size of the heart, which is a clinically relevant parameter because it's very correlated with the body mass index. So basically, just by looking at which general direction we were seeing in this data set of heart shapes, we found one principal component which was linked to the body mass index. So yes, we have an abstract mathematical geometric approach to describing this transformation, but the hope is that we will recover the usual clinical parameters and maybe even discover more clinical parameters. And so I think this is a very good instance of a pluridisciplinary approach because historically medicine and computer science have not been that linked. But now that we have more medical images being produced every day in hospitals and also more computing power to actually analyze these images and do machine learning on these images, now is a very good time to have both fields of mathematics and medicine or of computer science and medicine merging to see if we can establish a dialogue between the geometric parameters and the clinical parameters.
Can you elaborate a bit more on that example? What did the data set look like? Was it an image-based data set? How did you go from, presumably, again, some set of images in 2- or 3-dimensional Euclidean space, again, another assumption, to geometric representations? And then how exactly did you apply PCA to that to determine these deformations, right? The deformations and derive this size factor.
Yes. So originally it was an image data set, but we extracted, image of the heart, but we extracted heart surfaces in terms of meshes. So in order to do that, you have in medical imaging community what we call segmentation algorithm. So there are many that are available, and they basically do that. They are able to take an image and extract the surface of the heart. So for us, the starting point was this data set of meshed surfaces of the heart. In order to go from the surface, one data point, to the deformation, one data point, we use this template modelization in the sense that we took one heart shape and we named it the template. And so each of the other heart shapes, so heart surfaces, was a deformation from this template to the data point.
You arbitrarily picked a heart shape to which you called the template. I envisioned earlier that the template was derived in some way. Akin to an average or some statistical template.
Exactly. So and actually template shape estimation is the main point of my PhD thesis. So that's a whole subject on its whole. I wanted to simplify a little bit, but you're completely right. So in fact, the template shape and the deformations are jointly computed. So you have an iterative algorithm that is called template shape estimation that works as follows. First, you take all the heart surfaces and you register them. So you align them in order to correct.
Find a centroid and try to make them overlap as much as possible.
Exactly, yeah. So that the surface themselves, the meshes overlap as much as possible. This is called registration. After this registration step, you compute an average. If you're in images, you do that in terms of pixels. If you're with surfaces, you find the middle for each corresponding meshes. And so after the registration step, you have an averaging step. This averaging step gives you an initial estimate of the template. And then you iterate the algorithm. Now that you have an initial estimate of the template, you register again everybody, not among themselves, but to the template, and you average them again. You have a second estimate of the template. And you do that over and over again until you converge to a template. And so in the end, you have a template shape, and each single image or each single surface being described as a deformation from this template. Yeah, actually, as I said, my PhD thesis was exactly on this algorithm, because this is an algorithm that is very well known both in medical imaging community, but also in signal processing community, where you want to align signals and then compute an average of signals. So in terms of signals, you might imaging spikes for neurons or stuff like that, temporal signals.
Okay.
And so they also have, if they want to see the shape of a signal, they also often compute a template shape and do registration. So it's a very well-known algorithm in the field. And the goal of my PhD study was to analyze the statistical properties of this algorithm, which can be done using geometry, and which hadn't been done before.
And so I'm imagining if you've got this template heart and you've got a corpus of other heart meshes or representations, that one of the things that you might want to do is like find a distribution of the way that a heart, or hearts in general differ from the template, and that,
yes.
Part of what makes that difficult is in trying to do that in Euclidean geometry is that you have to do it in like at any given point on the surface a bunch of different directions. And is that part of what makes geometric models easier to apply here?
Yeah, so that's exactly what we want to do. We want to describe the variability, for example, in heart shape, and we do that on a geometric space. Not necessarily because it's going to be easier, but it's because it is what it makes sense. So if we go back, to the example when we were averaging two cities on the surface of the Earth, if we are computing a Euclidean average, then we get something that is not a city. Going to the heart now, if we want to compute an average of all the healthy heart, for example, to get a template healthy heart, if we were to do that using Euclidean geometry, we will get something that doesn't look like a heart at all. So it's more in order to be able to describe the variability of heart by summary statistics like a mean and then a standard deviation. We want these summary statistics to make sense. So we want the mean of heart surfaces to be a heart surface. And that's why we use geometric statistics.
Makes sense.
And then to describe the geometry of the heart shapes, we can do many things. So I'm taking the example of the mean heart shape, but then we can look at variations. So that's where PCA comes in. What are the healthy variations of a heart shape? For example, size can be a healthy variation of a heart shape. But then we can also look at clusters. And the intuition is that the different clusters that you might see will correspond. One will be for healthy heart shapes, and another one may be for a certain pathology that can be seen in a heart shape. And actually, this is what we do for brain shapes, where if you do that, a clustering on brain shapes, and you want to separate healthy brain shapes versus brain shapes with Alzheimer's disease, then you can easily separate that, because Alzheimer's disease is a disease that you can see on the brain shapes. So there is an atrophy of the cerebral cortex that changes the brain shapes.
How do you describe these types of geometric statistics in terms of, are there, different sets of distributions or kind of different fundamental laws? Like what What's different about the way things work in the geometric world compared to what we're used to?
Yes. So basically, every time that you had something that was linear in the Euclidean world, then you need to translate that into something that is not linear in the Riemannian world. And even the very basic operations don't work anymore. So if you're in a Euclidean space and you have 2 points on this Euclidean space, you can do a subtraction of a point to another and you get a vector. So if you have point A and point B, if you do B minus A, you get vector AB. Now, even this very simple operation, the subtraction, you cannot do it in Riemannian geometry. So this very operation has been translated to the Riemannian geometric framework, and we call that the logarithm. It's not linked to the logarithm as a function, it's just called like that. Okay. Same thing in the Euclidean world. If you have a point A, you can add it a vector, u, a plus u, and you get another point. Right. You use that vector to shoot from point A, and you arrive at another point. So the addition. This addition doesn't even exist in Riemannian geometry neither. Because if you imagine that you're on the surface of the Earth, if you shoot along a tangent vector and you see what you arrive, you're not going to be on the Earth. So you want to generalize this operation in order to do very basic computation in Riemannian geometry. And so I took the example of the subtraction, of the addition, basic operations that don't exist as is in Riemannian geometry, and that we needed to generalize. And in fact, the way that we need to generalize these very basic operations links to the fact that we have generalized optimization algorithm, for example. So if you think about an optimization algorithm, you're in a machine learning framework and you want to find the parameter theta that optimizes your criterion. Then when you do gradient descent, that's what you're doing. You have your current estimate of theta and you shoot along the gradient. So in Euclidean geometry, you have a point, which is theta, and you use a vector, which is the gradient, to shoot along it. So now this operation, which is addition of a vector to a point, we cannot do it in Riemannian geometry. I mean, now we can because we have generalized the addition, but we couldn't do it as is in Riemannian geometry. Otherwise, we would have gotten out of the space of parameters, just the same way as we would have gotten out of the surface of the Earth.
So we've generalized the addition, but we've also made an analogous construct to a vector that's, a curved vector on the surface, correct?
Yes, but in fact...
Yes, maybe?
Actually, in Riemannian geometry, we use the concept of tangent vectors. So if you take your curved space, like if you take the surface of the Earth, remember I said that Riemannian geometry was locally Euclidean. So on the surface of the Earth, if you are in your office on the Earth, then the Earth looks flat. Mm-hmm. So Riemannian geometry is locally Euclidean. And in fact, it means that at each point of a Riemannian manifold, so a curved space, there is a tangent space that locally approximates very well your curved space. And so actually we use vectors as well, because we use at the point of a curved space, we consider the tangent vectors at this point. And then we transform them into curved vector if you want. So we add a tangent vector to a point. This brings us to another point on the curved space through a curved vector. You can imagine it like that. But since we have so many tools in Euclidean geometry, we wanted also to bring these tools back on Riemannian geometry. And so we bring them back locally at each tangent space of the curved space.
There's some vector in this tangent space that gets projected onto the surface, and that's your Riemannian vector, so to speak.
Yes. That's the way. Yeah.
Butchering the terminology, of course.
No. Yeah.
That gives us a little bit of a foundation. Part of what you've been up to recently is building out a set of tools to make this a little bit more accessible. Can you talk a little bit about that work?
Yes. So yeah, as I said, I'm very passionate about geometry. And even though I learned geometry in theoretical physics, when I saw how it could be applied to computational anatomy and computational medicine, I really wanted to democratize the use of geometry. And so that's why, starting last year, I've started to build a Python package to be able to democratize geometry. So it's a package that is called Geomstats. It stands for Geometric Statistics. And basically, it allows you to do this addition and subtraction, so generalization of addition and subtraction on Riemannian spaces easily. It encapsulates the geometry so that you just have to think about, okay, I'm going to use the generalization of the addition. I'm going to use the generalization of the subtraction. And I wanted to do that because we have seen that actually in machine learning, a lot of spaces, data spaces, have geometric properties. For example, if you're looking at protein shapes and you want to describe the shape of a protein by the list of angles from one carbon of the carbon bone to another, then you have a list of angles that belong to a set of spheres. There are many ways and many examples in machine learning where data belong to geometric spaces. And so we wanted to give a package that allows people to do the computations on these geometric spaces. So we have implemented various spaces like hyperspheres, hyperbolic spaces, also space of matrices, for example, symmetric positive definite matrices or rotation matrices, etc., so that people could do proper averaging in these geometric spaces. So this is a Python package that is available on GitHub. And we're also currently writing a journal paper that explains the need and the use of this package for the machine learning community.
Interesting. So does Python support something like polymorphism where that would allow you to just kind of drop in and replace the operations provided by this package?
By plus and minus.
By plus and minus, yeah, exactly. Or do you have to kind of update your code to use the package?
Right now you have to update your code. It's true that it will be, a very interesting use of polymorphism. Right now we've given these operations their name, so exponential and logarithm, the name they have in mathematics, and it's up to the user to do the translation. But that's actually, an amazing idea. You could use polymorphism. But I guess we also don't want to completely hide the fact that it's geometric. Otherwise, people might forget about it. And then when they will run into bugs, then they won't understand what's going on. So, for example, remember the example of averaging two hard shapes. If you do that in the Euclidean way, you're going to get something that is not a hard shape. And this is not a bug of your code. This is not a precision problem. This error has a mathematical foundation. It's because the shape, the space of hard shapes is curved. So we don't want to completely hide the fact that there is geometry, but more encapsulate some subtle concept into a user-friendly environment. Yeah.
And so using this library to implement something like gradient descent, is it, besides from the fact that you're not using polymorphism, is it, essentially substituting your pluses and minuses with your exponents and logarithms?
Yes. So that's a way of thinking it. So the library, we've used it at 3 points at 3 levels in machine learning pipelines. So if you imagine a supervised learning, typical supervised learning pipeline where you have an input, it's X, and then you want to predict an output Y from this input X. And you do that by learning a function that can have a given parameter theta. Now we can put geometry at theta. So you say, the space of parameter, it's actually curved, and the gradient descent in that curved space will need to use or exponential and logarithm, which are the generalization of the addition and the subtraction. So that's one thing that we've put into the package, actually by creating our own version of Keras. So now when we have created this
all of Keras?
No. So we have we have re-implemented Keras. No. We have forked the Keras repository and just modified a little bit so that now you can add a parameter in some Keras function, this parameter is called manifold. And basically, if you say manifold is hypersphere, then it knows that instead of using the addition and subtraction, they will need to use, the code will need to use exponential and logarithm. So that's the first way of putting geometry in this supervised learning pipeline, is putting it for the space of the parameters theta. But now the way we've been using geometric statistics as well is by putting geometry on the space of the input x, but also on the space of the output y. And we've done an interesting example putting geometry on the space of the output y. So we did a regression on Lie groups. So the situation was as follows. It was, again, medical images, and we had slices of a brain volume, so actually a fetal brain volume. With fetal brain MRI, actually, you have a lot of motion, so the images are motion corrupted because the fetal moves in the belly of the mother may move as well. And so this is a case of medical images when if you take slices, then the slices are not going to be aligned within another. And when you want to reconstruct the 3D volume of the fetal brain, then you run into problems. And so what we've done using Geomstats is that for each slice of the fetal brain, we were predicting the optimal pose of this slice in the future reconstructed brain volume. And we did that using convolutional neural network, predicting a pose, where a pose is a translation, so it's the position of the slice in the 3D brain volume, and an orientation, a rotation, the rotation of the slice in the 3D brain volume. So we're able to tell which slice was supposed to be where in the future reconstructed 3D brain volume. And in order to do that, we put some geometry on the space of these positions and orientations, which was the space of the output for this supervised learning algorithm. Input is slice of brain, and output is position and orientation of this slice of brain. And by considering the fact that positions and orientations, they don't belong to your Euclidean space. They naturally belong to a curved space, which is a Lie group, is the space of translations and rotations. And though by taking into account the geometry of the space of the output of the supervised learning algorithm, we were able to get better brain volume reconstruction. So you can put geometry on the space of parameters. You can put geometry on the space of the inputs. You can put geometry on the space of the outputs, and you might increase the accuracy of your results.
In general, are these fundamental operations in the Riemannian space of the same order of complexity as the Euclidean, and as there are Euclidean analogs?
It will depend for which space, but what's interesting is that they're actually exactly the same on the infinitesimal level. So if you're really close, if you imagine your curved space and you close you imagine your curved space, which has a tangent space at a given point. If you're really close to this given point, then using your curved vector or your tangent vector is the same. So at the infinitesimal scale, yeah, they're exactly the same.
I'm wondering if you've ever tried to apply this someplace where, just to try it and were surprised that it actually works, or are you usually applying this because you have a strong intuition based on the problem that you should apply it?
No, usually it's based on a strong intuition. I'm trying to think. Yeah, I think it's more the second scenario.
I was just wondering if there's, if there are problems that might have some latent geometricness to them that we don't know, and if you could, now that you've made this easy with a library, if we could just apply it willy-nilly to see if that has some value.
Yeah. So I think one set of problems is every time you're dealing with rotations and translation, but especially rotations. So rotation is a very intuitive geometric example because we have an intuition of how it works. You can rotate an object. And even if it's simple, it appears in so many fields. One example is in medical imaging. When you want to register or align two shapes, you're rotating one shape to match as closely as possible the other shape. but also in robotics, when you want to control a robotic arm to do such and such, you want to move it in space, but you may also want to rotate the robotic hand that is at the end of the arm. So rotations is, even if it's simple, it's a very good example of a geometric space. And a lot of people haven't been considering the geometry of this rotation space. And so this is an example where it actually makes a real difference. And we've shown it with this supervised learning approach, where we are able to reconstruct better brain volumes taking into account the geometry of that space.
Okay, what I'm hearing is that as opposed to just kind of throwing this approach at a given problem from a modeling perspective, because it's easier now that we've got Geomstats, rather use it as an opportunity to think about where geometric statistics might apply, or if it might apply to the problem more deeply than you might otherwise, because now if it does, you've got an easier way to use that information.
Yeah, exactly. And that's the whole point of the paper that we are writing right now. So we do a review of geometry in machine learning, because our feeling is that a lot of people are using geometric data spaces. It might be an intuitive space like the space of rotations, but sometimes it's a more abstract space like a hyperbolic space, or the space of symmetric positive definite matrices, which has a geometric touch, but people don't often use that. So the first goal of the paper is to do a review and be like, oh, in that field, in fact, you have some geometry. With this data, in fact, you have some geometry. And then once we've convinced the people that deep down their data space is curved, then we tell them with Geomstats which tools they can use. And a very important set of tools that they can use is the set of metrics. So if you have a curved space and you want to measure the distance between two elements of this curved space, you need to follow the curvature of the space and take the length of the shortest curve that links these 2 points. So we call that a geodesic. It means that the distance between 2 points in a curved space is defined as the length of the geodesic. Mm-hmm. And this means that if you are using loss functions, if you are learning on a geometric space, the loss functions that you should use, which is the distance between the ground truths and the prediction,
is the geodesic.
Exactly. You should use a geodesic distance, because you will take into account the geometry of your space. And so that's what Geomstat is about, is first telling people, oh, your space is geometric. You should have a look at this geodesic distance, because it will be more suited for your problem.
What's next in this line of research?
So in terms of implementation, so Geomstats has been around for a year now, and we are in development. So we are currently developing different backends. So we want Geomstat, since we want to apply it to machine learning, we want Geomstat to be able to be used on GPU. So we are currently implementing TensorFlow backend and also PyTorch backend. So this is from an implementation point of view. And now the goal will be to use Geomstat. So for me, to study organ shapes, but also other kind of shapes. So initially, I was looking at brain shapes or heart shapes. Now I'd like to go into smaller scales and maybe look at cell shapes and protein shapes, and actually use the tools that we've developed to look at these statistics on these new kinds of shapes.
Sounds fantastic. Well, Nina, thanks so much for taking the time to chat with us about this really interesting work.
Thank you very much.
All right, everyone, that's our show for today. For more information on Nina or any of the topics covered in this episode, visit twimlai.com/talk/196. If you're a fan of the podcast and you haven't already done so, or you're a new listener and you like what you hear, visit your Apple or Google podcast app and leave us a 5-star rating and review. Your reviews are super helpful, and they inspire us to create more and better content, as well as help new listeners find the show. Thanks again to our friends at IBM for their sponsorship of this episode. Be sure to check out the IBM developer portal at ibm.biz/MLAI podcast. As always, thanks so much for listening, and catch you next time.